Okay, hello, welcome back everyone. This is the module 3.2. It's gonna be part 1. We're continuing with some of the discussion from the previous module. In this particular part, we'll introduce the idea of chemotaxis, and we can control certain properties and behavior based on movement due to chemical gradients. I'll try to be short in this part because this is an idea that Gilberto will come back over later today. But I still wanted to have some time to introduce the basics before Gilberto introduces a more complicated model. Just as a reminder, the presentation is being recorded and live streamed. As I mentioned, this is module 3.2 is a vascular tumor simulation, but we're running over some of the stuff that we left behind in the previous module. I'll try to be short and hand it back to Juliano after introducing chemotaxis. So what I'll do in this part of the module is I'll introduce the idea of cell movement due to chemical gradients. And I will show how this can be implemented in CompuCell on a linear gradient and how we can construct a cool and very simple simulation of bacterial movement in a nutrient that is fixed to, let's say, extracellular matrix. So biological cells alter some of the behaviors that cells alter due to or in response to signals and gradients. We saw earlier that cells can do this, can control cell division and proliferation due to changes in signals. Another type of behaviors that cells can change is movement. We will and there are different signals that cells can react to. They can react to how rigid their environment is, and we call this deutotaxis. They can react to electrical fields. They can react to changes in temperature, moving, let's say, away from areas that are too hot or too cold, and they can also move in areas that are high or low in, let's say, light sources. But in general, since we have introduced the idea of the chemical field, we can readily implement in CompuCell cell movement resulting from an exterior factor due to the gradients of some chemical field, and we will call this chemotaxis. Chemotaxis is when is the movement of cells from due to exposure of chemical gradients, and these are ubiquitous in biology. A classical example is the response of discotyledon to sources of CAMP. And this individual movement of cells due to the gradients lead to very interesting large-scale behaviors. And I posted a couple of links in the slide deck that show examples of cells chemotaxing due to some signals that have been added to the medium in which they live or move. So to model chemotaxis, all we need to take into consideration, or all we need to think about, is the fact that cells will move in response to how the gradient of the field is, or the chemical they are in is. Such that if, for example, the gradient is steeper, right, or the concentration is changing faster, then we will expect our cells to move faster up that chemical gradient. If the gradient is very shallow, then it's harder for the cell to detect that gradient, and so the cells will move a little bit slower up that gradient. In CompuCell, we modeled that by adding an additional term to our energy terms, what we call the the chemotaxis constraint, and we control that chemotaxin by adding this lambda chemo that controls how sensitive the cell is to the gradient. So there's two parts to the force exerted over cells due to the gradient. One is the steepness of the gradient. If the cell is steep, if the gradient is very shallow, cells don't move that fast, as opposed to if it's very steep. But also the sensitivity that we control through the lambda chemotaxis. The cell can be in a steep gradient, but it's not, if it's not sensitive to that gradient, then it won't move up to the gradient. But if it's the cells is very sensitive, then it will move up to the gradient. So it's a combination of the sensitivity and the steepness of the gradient that it will induce the cell movement. Right, this is the same idea. We call this force, or this energy term, the chemotaxis effective energy. Notice that if the lambda chemo is negative, if it's negative, what our cell will do is move from areas of high concentration to areas of low concentration, in which case the field is acting as a chemorepulsant. If the lambda chemotaxis is positive, then our cell will move up the gradient, in which case our chemical field is a chemoattractant. There's multiple ways in we can implement chemotaxis in CompuCell. For the purpose of this module, we will do the simplest type of chemotaxis implementation, which is done in the XML specification. This is sort of like the code that we will have to fill up. We'll have to specify what the name of the field is that will cause our cells to move, what the type of the cell is that it will be moving, and then the lambda chemotaxis, as described in the previous slides. So for this exercise, what we will do is that we will create a we will create a simulation domain, and then we will add a chemical gradient that decrease with a linear decrease, and this is based on the presentations from yesterday. Again, for those of you who weren't able to be with us yesterday, I would direct you to the modules, the discussion on this, the modules yesterday, where we showed how to implement where we can implement a linear gradient based on the properties of the field at the boundaries. Then what we will do is, after creating a linear gradient and initializing a single cell, we will introduce the Chemotaxis plugin, and we specify the lambda chemotaxis. And then we will plot the position of the center of mass of our cell as of in the X domain, and we'll run the simulation for different values of the lambda chemotaxis. For these first parts, first part 1 and 2, I'm not gonna go into detail because, again, this is something that was built up from the presentation yesterday. But I've already produced the code. If you wanna produce it by yourself from scratch, all you need to do is to run your simulation, to create a new project. Let's call it Chemotaxis. I'm sorry, I'm not sharing my full screen, I'm sorry. So I'm creating a new simulation. And I'm calling it Chemotaxis. I'm sorry, I have to choose the right directory to create it. And then I said that we are gonna set a 200 by a 200 lattice. I'm gonna create a no flux in this case, but it doesn't matter at this point because we're gonna stop the simulation before our cell reaches the edges. I'm gonna use the Blob Initializer to start our cells, to initialize our cells. I'm gonna create a single cell type called cell. Again, pixel copy of 3, I prefer, I keep forgetting about it. But yeah, it's always preferable to use a pixel copy range of 3. I use a cell type called cell. Again, I have to create a field, let's call it here nutrient. And use the diffusion solver FE. And then here I will select contact, chemotaxis, volume flex, center of mass. I need to make sure that I have it enabled so I can actually see the plot the center of mass of my cell. When I've selected chemotaxis, when I hit next, instead of ending the wizard, I'm gonna have an option to specify what the Chemotaxis plugin form it will be. And I said that we will have let's start with a lambda of 0 because we don't have our cells to move, and we'll modify directly into our XML. And the cell type we want is our cell type cell to move up the nutrient field. And we're just gonna use regular chemotaxis for this example. And then once I do that, I can finish my simulation. And this is the same as exercise 315. Okay. So when I load my XML, I can see now that in the XML, and this is based on yesterday, that's why I'm not discussing it in detail today, but I'm creating, I am setting the conditions such that I have a linear gradient starting at one edge and ending on the other edge. Yes, the Chemotaxis Towards means when cells are in contact with, you can control what happens to cells when they are in contact with other cells in terms of the chemotaxis. So if I specify that the chemotax towards medium, that means that once cells has reached other cell types, they might stop chemotaxing or moving. So I have in Chemotaxis Towards, I have to specify which cells once my cell is in contact with cells, which cells inhibit their chemotaxis and which cells do not. Since in this particular case, we just have one cell and it's surrounded by medium, I didn't care to specify that, but that's a little bit for more complicated. For more complicated simulations. So again, I'm not gonna go into the details of the chemical field specification because that's discussed yesterday, but those specifications will guarantee that you start your simulation with a linear gradient and with that cell at the edge of your simulation domain. And now in that XML, you can see that we have the Chemotaxis plugin. And if you started with lambda 0, you should see it here. If I saw in the comment, someone says that it's not loaded into the XML, as you can always come back to CC3DML plugin and hit on Chemotaxis, and then that will load the Chemotaxis plugin for you. If you forgot to specify, let's say, wizard. So far, what I've done is some parts based on yesterday, I created a linear gradient and I've added a single cell at the edge of the simulation domain. And now I specified that my cell has a lambda of 500. So its name, how do I specify what field is responding to? It's called field here. It's just, I'm sorry, in the example that I showed, I call it nutrient, but in this case, I call it field. That was from yesterday. But I specify what what field the cell responds to in this part of the plugin. So this says that my cell type cell is responding to the field, unfortunate choice of name, with a lambda chemotaxis of 500. And that's what's explained in this simulation. Now, if I run that simulation, what I'll see is myself moving from one edge of the simulation domain to the other edge of the simulation domain. Yes, I can certainly show the XML. Remember that the XML has that part where I'm creating the linear gradient, and I'm actually not going into the details of that. That's why I wanted to share the base code with you. But what is important for the purpose of this module is that we specify the Chemotaxis plugin. Just make sure that the name of the field here and here matches the name of the field the cell is responding to inside the Chemotaxis plugin. So when I start the simulation, I can see that my cell stars. What should I put in Chemotaxis Towards? You can put medium, or you can leave it blank. I do not have it in my my specification. But as I said, you can put medium because it means that it's gonna move through the medium to get up the gradient field, the gradient of the field. So now I can show my linear gradient, and I can see myself. And if I execute the simulation, I can see myself moving up that gradient. Right. James is right. That is the right definition is of the Chemotaxis Towards. It specifies the surfaces on which the cell is going to attempt to move towards. So if I specify medium, it means that it will try to move over medium. If I want to be able to chemotax over other cells as well, then I will have to specify what cell types my cell is able to move. Right, that's exactly what James is specifying there. So in this particular case, I can see that my cell is moving up the gradient, but it's moving very slow. If I increase the chemotaxis, the lambda chemotaxis, which I can do here in the model editor, then I should see my cell moving faster up that gradient. So now I can see my cell actually moving much faster up the gradient. And if I set it to 5,000, now I can see my cell moving much faster up the gradient. And I'm gonna stop my simulation there. Yes, that's what I'm doing. To see the cell on top of the gradient, you select the field in your visualization window, but just make sure that your cell borders are checked up. If your cell borders are unchecked, you won't be able to see the cell on top of the gradient. Okay, now in the next part, what I'll do is I wanna plot what the center, I wanna quantify the movement of my cell. So I'm gonna plot the center of mass of my cell as a function of the position. And again, this is a refresher. I create a plot window in the start function of my Steppable. And then what I do is I create a data series called POS. And then in the step function, I iterate over my cell list and I plot the time and the position of the center of mass on the X direction. And I plotted just on the X direction because that is the direction of the gradient. On the Y-axis, the cell might move up and down, but that's just gonna be due to random cell membrane fluctuations and not due to the chemotaxis. So I just plot the X-axis to see the movement due to the chemotaxis. And now if I execute my full code with the plot, what I should see is that now I can see how the center of mass of my cell is changing due to the chemotaxis, and it's decreasing, right, because it's moving left. And you can see that there are some fluctuations up and down here. Anyone has a guess as to why that is? Any guess why are we seeing this wiggle in the position? So what's happening here is that, right, because the cell movement is right, because the cell movement is composed of two components, right? I have the cell movement due to random fluctuations in the membrane, and I have the cell movement due to chemotaxis. And if the movement due to chemotaxis is relatively small, then what I should see in my movement is both the combination of the random fluctuations in the membrane plus the chemotaxis. If I were to increase the chemotaxis, the lambda chemotaxis, I'm sorry, I stopped it, but I shouldn't have. Okay, I didn't stop it. So if I were to increase the lambda chemotaxis, let's do it to 3,000. Then the cell is gonna move much faster, right? Because the velocity of the cell is the slope of this curve. And now is there's less wiggle in that movement, and that is due to the fact that the contribution of the movement due to chemotaxis is much bigger now compared to the random fluctuations. And you can see that the velocity changed when I changed my chemotaxis. The velocity here was about, let's say, 20 pixels per 100 Monte Carlo step. Here it was about 100 pixels over 100 Monte Carlo steps. Okay. So I'm gonna leave this to you to play so you can restart the simulation with different values of the lambda chemotaxis. You can modify them either on the model editor, or you can come here to the plugin specification to change it. Yes, so the chemotaxis is indifferent as to where the field is coming from, or even if the field has a particular shape. In this particular case, we set the shape to be linear, but the cell can react to any type of shape of the chemical gradient or what the source of that chemical gradient is. So I'm gonna move on to the next exercise because this I'm gonna try to treat it as an example so I can hand back to Juliano for the avascular tumor. But in this case, what we will do is that we will construct we will build a simulation that it resembles bacterial movement with a nutrient that is bound to, let's say, an extracellular matrix. And the way we will do that is that we will have, we will initialize a simulation with 100 by 100 lattice and periodic boundary conditions for the cells. We will initialize a single cell type, amoeba or bacteria, and a single field nutrient, and we will have contact, chemotaxis, and volume constraints. Then in the XML, for the field, we would set the global and decay coefficients to be 0. So that will mean that we will have whatever field is there won't diffuse and won't decay. And this is how we model this matrix bound nutrient. But we will specify different diffusion coefficient and decay coefficient inside the cell. And this, again, this takes us back to yesterday, where we were specifying diffusion coefficients and decay coefficients by cell type. We will set the field boundary conditions to be periodic, and we will initialize the concentration to be 1 everywhere. So this is with these initial conditions and diffusion and decay coefficients, what we should see is that our full simulation domain has an initial concentration of 1, and then we will place one cell in the center of that simulation domain and let it move due to the chemical gradient. But the chemical gradient will be created by the cell itself, the cell itself as it moves through the simulation domain, because otherwise the chemical field does not diffuse or does not decay. So what I'll do is I'll walk you through that code. This is exercise 3.316. So in the XML, we have created our simulation with our simulation domain as specified in the instructions. We have initialized our cell, and we have specified our volume constraint here in the XML because we're not changing it. so we can specify it here. We have the constant energies, and then we have specified a chemical field called morphogen that has a global diffusion constant of 0, a global decay constant of 0. So that's how we model the nutrient-bound, matrix-bound nutrient, but it actually decays inside the cell. It diffuses and decays inside the cell. And we've set up the field to have an initial concentration of 1, and then we have specified that our cell can move due to can chemotax in this gradient with a lambda chemotaxis of 200. And there is really nothing else that we need to specify this simulation. It's very simple. It's complicated conceptually, but simple to implement, and actually produces a very interesting simulation. Let's run it here. So we start with a cell in the center of the simulation domain. And as I said, there is field, the quantity of the field is 1 everywhere. And I started the cell, and once I start the simulation, the cell starts consuming from that field as it moves and chemotax in the field. Remember, the reason it's not diffusing inwards here is because it's membrane bound, and I set that by setting the diffusion coefficient to be 0. But inside the cell, the chemical field can actually diffuse and decay. And that's why the cell can construct its own gradient. And you can see that it's very interesting that the cell has both types of like persistent movement, and then some type of tumbling and moving around. So it persists on one direction, it tumbles a little bit, and that tumbling is due to random membrane fluctuations, and it continues moving. But you can also see that the cell avoids region it has already been to, because it already consumed the available nutrients in that region. Okay, and what I'll do is I'll stop here. I've been talking for half an hour now, and I want to give Juliano time to present his avascular tumor demo, but I'll be happy to go over this particular simulation. I know some people are interested in this type of simulation in the hackathon, and this is a nice example of how it can be implemented rather easily. Yes, it is because the cell eats up. In this particular case, we implemented it by setting some decay inside the cell, but we could also do it by setting it to be some uptake that we didn't do, just to keep the simulation simple. But yes, when I say creates its own gradient, it's because the cell is taking up or eating up the nutrient. I'll stop here, and I'll hand back to Juliano now.
Hello again, everyone. So we'll try to get a avascular tumor demo done using the concepts of diffusion that we were talking about. I'm sorry if I go a bit fast today, but I have less time than I expected. So
Juliano, it's okay. If you need more time, I would make sure everybody gets through it. And if we move some material from this afternoon to tomorrow, I think it's better to take the time we need so everybody follows.
Okay. Okay. Okay, so most of the lecture is well, going to be exercises building up the simulation of a vascular tumor. We are going to have 3 cell types. We are going to have cell division. We are going to have cells uptaking nutrient from a chemical field. We are going to see how to kill cells and how to mutate cells, hopefully. So in a avascular tumor, we see 3 layers of cell behaviors, with proliferating cells outside where they have enough oxygen and nutrient, then quiescent cells where there isn't so much, and finally necrotic cells when, well, they don't have enough to live. And as we have the diffusion parameters, we can set those so that we know where, more or less, inside the tumor, the chemical is going to be at a certain level. So in this image here, we can see, I don't know, 4, 5 cells in that are still proliferating, at least according to Garcia and all. And we're going to use that to define our diffusion constants of D and gamma. And we're going to define those in the natural units of pixels and MCS. Another thing that we'll do is, instead of having the nutrients come from the very edges of the simulation, we are going to have the whole medium be the supplier of nutrient. That way, we're going to see the tumor cell self-limit itself. And I think the resulting movies are quite cool. So actually, let's get properly started. So I already have Threaded open here on NanoHub. And as usual, we are going to start a new project. I'm going to select where I want to save it. I'm going to create a new folder here. 3, 2. Oh, I need to actually create the folder. There we go. And I'm going to call my simulation Avasc Tumor for short. I have to drag these things to make them show properly. We are going to leave the dimensions, the default of 256, but we are going to use periodic X and Y. And Josh says that it's best to have a pixel copy range of 3. I personally prefer 2. So a bit of a difference. And instead of having the rectangular slab, we are going to use the Blob Initializer. After all, our tumor is roundish, so it makes sense to start with something that is round. We have 3 cell types. The proliferating cells, which I'm going to call Prolif for short. The quiescent cells, and I'm again shortening, and the necrotic cells. And we are going to see how to change cell types in between those based on the chemical field that they are exposed to. In reality, as this figure implies, we have both waste and nutrients in different gradients. And not only nutrients, but we also have oxygen, and not only waste, but we have several types of waste. But to keep things simple, we are gonna govern the behavior with only one field for the nutrient. And we can see that that's enough to get the behaviors we want. And again, we can always complicate things after we get something working. So only one chemical field, nutrient, and I'm using the default solver. As for plugins, we're going to use contact as usual. We are going to use secretion for when we do the uptake. Uptake is just negative secretion. And we also have cell division, so we select mitosis. And now we only have the option of volume local flex. We cannot use the volume non-local flex. And that's the final plugin we're going to use. So contact, secretion, mitosis, volume local facts, and center of mass, but that's selected by default. And now we come to secretion. So I've mentioned that we're going to have medium be our source. And this allows us to set the XML properly for that easily enough. So at least for me, I already have nutrient selected and I already have medium selected there. And what I'm going to say is that it's going to be set to 100 for 100% of nutrient. And I'm selecting constant concentration there. So I'm imagining that the influx of nutrients is enough always to keep it level. Now we actually have to click add entry here and it shows up. So again, I already had nutrient and medium selected. I set 100 there and I selected constant concentration and add entry. And if you made a mistake, you can clear table here. And that's it. So from the start, well, I gave it a name and a location. I left the dimensions default, periodic, X and Y, copy range of 2, but shouldn't change much by using 3. 3 cell types, prolif, quiescent, and necro. 1 field of nutrient. Contact, secretion, mitosis, volume local, and center of mass. Nutrient secretion of 100 by medium, and that's set here, selecting the field, selecting medium, 100, constant concentration, add entry. And that's it for configuration. If we told Compisol to run this, it would run, but to edit by default pastes a bunch of stuff that we are not actually going to use, like here on the nutrient field. It has all the code to have different cells with different diffusion coefficients. But for now, we are gonna keep everything the same. So I'm just going to delete those tags. And there's, oh yeah, so after deleting those tags, we come to our first decision for the diffusion constant and decay constant. So I like my cells to be 64 pixels, but that's me. And going by that image that I showed earlier, we have about 4 cells deep until they transition. So I'm gonna set things up such that our diffusion length is about 4 cells. So if cells being 64 pixels and roundish, their diameter is 8 pixels, not really, but it's fine. And so we'd want our diffusion length to be 32 pixels. And since the diffusion constant and the decay constant are related with, well, the diffusion length is the square root of the diffusion constant divided by the decay constant. So I just rearranged things here and I already squared the diffusion length. We want a diffusion constant that is about, so let me type it here maybe. So the diffusion length is the square root of d over gamma. So if I pass the square root to the other side and gamma to the other side, I have that d is dl squared times gamma. And we know that DL should be 32 pixels and 32 squared is 1064. Gamma is the decay constant. And so, but 1024 is about 1000. So we want our diffusion constant to be 1000 times greater than the decay, which is close to the defaults here. And I could just set this to e to the -4 and we'd be good to go. But in that case, the diffusion would be a bit slow. So as the tumor consumes nutrient, it would take longer for nutrient to come in, and that could have unintended consequences. And well, I've set the parameter I have in the presentation using 10 and 0.01. You could use 1 and 0.04 or things like that. But then the thresholds that you need to use to control the cell behavior would be different. Next thing the next thing I already did, which was deleting all of the diffusion coefficients for the cells individually. We are only having the global one. And we are going to start our simulation with, we are going to use the initial concentration expression. And we are going to start with 100 units of nutrient everywhere. So I'm going to uncomment this line and replace that x times y by 100. Okay. And we can also see here that inside the diffusion solver, there is some secretion data, but there's also the secretion plugin here, kind of redundant. And cells should consume nutrient. They shouldn't secrete nutrient, right? So I'm just going to comment these lines out. And I'm pretty sure that we do need the secretion data tags inside the diffusion solver for things to work properly. So again, I'm gonna select those lines and add it and block comment, since commenting on XML is cumbersome. And since we have medium secreting the nutrient, medium is our boundary for the chemical field. And so what we are going to use here for boundary conditions for the chemicals is periodic in both X and Y. So again, I'm going to comment that lines that set constant value or constant derivative for X and Y. And I'm going to uncomment the periodic tag there and here. Okay, so again, everything that I did in the diffusion plugin. First, I set my diffusion constant to be 10 and my decay constant to be 0.01. I've set the initial concentration to be 100 everywhere. I've removed the extra diffusion and decay constants for each cell type. And I remove the secretion of nutrient by cells, which doesn't make sense. And I've changed the boundary conditions to be periodic in X and Y. And one final change that we are going to do here in the XML is to the Blob Initializer, which is first to have the cells begin with 8 pixels, because that's what I like. And instead of starting the simulation with randomly placed prolif, true, I meant 1 extra 0. These should be 1,000 times gamma, is that right? Yep, yeah, no, you're right. Yep, it should be 2, not 3 here. Thank you. You should have just typed over, copied from my slide. Trust my slides, not me. But yeah, and then in the Blob Initializer, we have all cell types here, but we are going to start with all tumor cells being proliferating, gives the tumor a chance. But one small parenthesis that I could make here is that if you want, so if I have prolif and quiesce here once each one, I'm gonna have half the cells be proliferating and half be quiescent. But if I have proliferating twice, in this case, 2/3 of the cells would be proliferating and 1/3 would be quiescent. And in this case would be 3/4, 4/5, etc. But I want 100% to be proliferating. And if now we go to the Steppables, because we selected mitosis, we can see that the Steppable structure is a bit different. There are 3 Steppables, one for the constraints, one for growth, which is already active even though we didn't select it, and the mitosis. So first, we don't want our cells to be 25 pixels, we want them to be 64. We could leave lambda to be 2, but I prefer 8. And I know that the simulation will work with 8, but I don't really see a reason why it wouldn't work with 2. And here in the growth, we're gonna leave as is. We're gonna let things grow for now. But here in mitosis, we already have a problem because our cells are starting with 64 pixels. So if I just show it to you, what would happen here? Start with our cells all pretty and nice there. And if I step it once, they all immediately divide because the condition for division was assuming a target volume of 25 instead of 64. So instead of 50, 2 times 64. And we can see that the other thing that happened here was that half of the cells changed type after division. And we don't want that behavior, at least to start, for this simulation. And that behavior happens here. So I'm just going to, again, comment these lines out. And now if I do it again, and we go. Okay, things look all right. My cells are there and they're still growing because I left growth alone. And one thing that I'm going to do, and we already saw some division there, and I'm gonna have a second graphics here for the chemical field. So we can already see how the tumor is gonna self-limit because we have 100 everywhere in medium and it's going to stay that way. But inside the tumor, things are actually going down. Yeah, and here's what we are seeing here. Okay, so we need cells to change their type based on them having enough nutrient available. So we want one transition from proliferating to quiescent, one transition from quiescent back to proliferating, and another transition from, well, from quiescent to necrotic, but really should be from anything to necrotic, but quiescent to necrotic will work in our case. And we also want the proliferating quiescent and quiescent proliferating transitions to be not at the same level, because if you imagine that if the concentration is at that level, random fluctuations can make cells flip-flop between the two behaviors. So we're gonna set the quiescent to proliferating to be a bit higher than the other one. So it takes a bit more effort to begin proliferating. So we already have, we're gonna do this in the growth steppable since we already have a step function here. And we are going to replace this loop over everything with 2 loops, one over proliferating and one over quiescent. So I'm gonna comment out this loop here. And I'm going to add my 2 loops. So first, asking to edit how to visit cells of a given type. And again, it pastes this. We could do both types at the same time, but it's best to do one at a time for this simulation. It doesn't matter which Steppable we put it in, as long as it's inside the step function of the Steppable. So in this first loop, I'm gonna go over the proliferating cells. And instead of asking to edit again, I'm just going to copy the loop and just change this to Quiescent for Quiescent cells. And yeah, to edit, and so now we actually need to measure the field and do something with that measurement. Thankfully, if we look down here, to edit already pasted what we need. So it pasted this command that grabs the field, all the values of it, and this command that actually gets the field at the center of mass of the cell. So we can just copy from here. First, I'm gonna copy the field definition to be before our loops. After all, we are gonna use this object field here in the loops. I just need to change the chemical field name to be nutrient. In this case, so one inconsistent thing is that cell types need to be all caps always, but fields need to be as you type them here. So here I have nutrient all lowercase NUTR actually. So in here I have NUTR as well, lowercase. And then to get the concentration at center of mass, I'm gonna copy this line here. And I'm going to paste it inside both of my loops. So one thing that I did here was I was printing the chemical concentration, but one thing that I forgot is that in NanoHub, unfortunately, we can't see the prints. If you're doing it locally, you could just print this. So what we are going to do is instead is remove those prints by commenting them out. And then we are gonna add a cell dictionary for that value there. So cell dict conc for concentration. And that should be equal to concentration at COM for center of mass. And I'm going to copy that here too. And now we can actually visualize those concentrations by adding an extra field. And extra fields can be added in any init of any steppable, and CompuCell will figure things out. So I'm coming here into the init of the growth steppable, but I could do it here as well, as long as it is in an init function. And I'm gonna ask to edit how to do extra fields, automatic tracking. We have these old commands for backwards compatibility, but they are cumbersome. And this is very not cumbersome. So I just click track scalar attribute. And what this command does is that it's looking for this attribute name inside the cell dictionaries and is going to display it in player. So the attribute you need to look for, in my case, is conc. And I'm gonna also name my field conc. And now if I run, I have both nutrient here, but I could also add another window and have conc. Now I'm gonna hit dial. I'm gonna go over everything again. So now we can visualize the concentration that they're sensing at their center of mass. So what I did in Python was, first, I removed, where was it? Here. I removed, conc is just the concentration that I measured of the nutrient field. They look similar, but because I'm measuring the concentration at the center of mass, only we can see that the jumps are discrete, whereas in the actual chemical field, it's a slow gradient. There you go. So in the Steppables, what I did was I changed the constraints in the constraint initializer to be 64 and 8. I then changed the trigger for cell division to be 128 pixels instead of 50. And I removed the change of type with cell division. And then I removed the loop in the growth Steppable over all cells and added 2 loops, one for the proliferating cells and one for the quiescent cells. And then I noticed that there was already some code here that I actually could use. And I copied this, well, first I copied this declaration of the field values here. So I have the field values of the nutrient field in the handle field. And I also copied over the command to measure at the center of mass of the cell. And I'm passing that measurement to this dictionary here. And then I came back to the init function and I asked to edit how to track a custom field automatically here. And as you can see, you could also do vector cell attributes. So for instance, for bias yesterday, we could have an extra field that actually displays the bias vector. And exercise pre-launch. Yes, the code is available at the demos files. Yes, good question. It's here, and it is how the code is going to look at the end. So you can use that to cheat a little bit if you want or need to. No shame in that. Let me actually just make your life easier. Okay. So next thing is actually to define, well, the thresholds of each of the transitions. I did it here in the growth table, but I actually don't want to do that now. I want to do it in the constraint initializer since we have it. And this way I can show you how to use the Steppable shared dictionary thingy, which is very useful. So first things first, I'm gonna define the proliferating quiescent transition to be a fraction of 100, the threshold. And the threshold that I selected is dividing by the half of E. And that's just a property of the diffusion length. And so A diffusion length, the concentration is gonna fall by product of E, but I'm adjusting it a little bit because I know that works better. So here I'm using NumPy, so I actually need to in the start. Yeah, in the start, I think it wouldn't work in the init, but I'm not sure. So I'm gonna import NumPy as NP. So I'm gonna have 100 divided by half of E. And I actually need to remember to multiply my numbers. And then I'm defining the QP transition to be just a bit higher than the other one. So an easy way is to just multiply PQ by a bit more than 1. And finally, the transition to necrotic, which is QN, is going to be 100 divided by E full E. And now we actually need to save all of these numbers into something that we can access in the growth steppable. And again, Twedit knows how. CC3 Python, this one I don't remember exactly where it is, but I think it's in simulation. Yes. So CC3 Python simulation, shared steppable dictionary. So the shared steppable vars is the dictionary that all steppables share and know about and coordinate. So in here, I'm gonna add a key for each of them, which I'm just going to use the same variable name and set that to be PQ. And same for the other ones. If someone is curious how I multiplied my line that fast, it's Control D. It copies the line that you are in below it. Again, I imported NumPy. I defined my numbers. I asked to edit, what was the name of that dictionary that all steppables know again? Which is in CC3 Python simulation shared dictionary. And just giving them keys and the numbers. So now we actually have everything we need to have ourselves make decisions about their life. So if we go back here to the growth steppable, in our loop over proliferating cells, we're gonna make them quiescent by adding a if statement. Oh, it's not there? The dictionary exists. It's just that Twedit doesn't know how in that case. Let's see if I can copy this outside of. Well. That's the name of the dictionary. So here in the loop over proliferating cells, I'm gonna tell them that if the value here in this dictionary with key conc is less than the number here in this shared steppable vars, then it should change its type. And type is a cell property that is easy to remember. But again, if you don't, and I actually don't sometimes, it's CC3D Python cell attributes cell type. So now then we know that cell type is accessed by cell.type. So we actually don't care what the value of cell type is right now. What we care is that to change it from whatever it is, which is prolif, to quiesce. Now just to test, I'm gonna run this and we are gonna see some cells become quiescent eventually. Yep, there we go. And I'm going to do a similar thing with the quiescent loop, but in this case, it would be another threshold, but I can just copy over this if and just change the key here from PQ to, well, first let's do the reverse, so QP. And in this case, we're going to change the cell type from whatever it is to prolif. And now we need a second if in case this isn't true. So I'm gonna add a elif, well, not capital, elif. I'm just going to, well, one thing that I was going to make as a mistake here, I kept the less than. I shouldn't have kept the less than. There should be a greater than, since it's going back into high levels of concentration, right? But now I can safely copy this one with the less than, since this if is going to turn the cells necrotic. So this transition is QN. Then cell type is going to equal self dot necro. Okay, so from the top, what I did was I came back to the constraint initializer. I defined my threshold numbers here. I asked to edit how to access the dictionary, but it's also in chat now, so you can just copy from there. And it, copied those numbers into different keys of this dictionary. And then down here on the loops, I'm using the numbers associated with those keys to change cell type. So in the case of the proliferating cells, if the concentration they are sensing is below this number, they become quiescent. In the case of the quiescent cells, if the concentration that they are sensing is above this number, they become proliferating again. And if the concentration that they are sensing is below this other number, they become necrotic. Now, if I run this again, we already are going to see the 3 layers forming. Yeah, another window here for the conc and tile. Sure. Just, yeah. So people that done it, you can let it run and you see the 3 layers already. Actually, let me make this a bit bigger.
Could you define the shared dictionary in the init functional other steppables?
Yep.
So Was there any specific reason that you put at the first one? I mean, the Python starts from reading from the top, you mean?
Yeah, I've put it here because this steppable is named constraint initializer. So I thought it would make sense to initialize a constraint here.
Okay.
But we could have just done it all here in growth steppable. And yes, we couldn't make the transition between cell types stochastic. I would still make it stochastic dependent at least a little bit on concentration, but we could have, instead of having a one threshold for all the cells, we could have it defined on a cell basis and have, instead of having the same number, varied a bit randomly. And actually that's a exercise later when we add mutation. So if I just come back here, I still don't have the 3 layers. That's fine. Yep. Yes, I'm gonna upload what I write here in the class later there, but it looks a bit different, but not really. The only difference is that things have different handles, but it's exactly the same code. So now, well, we removed growth, but we can add that back. So we want the proliferating cells to grow. So we could naively just, add it here before the if, but that would mean that some cells that turned quiescent would also grow. That's not really what we want. So what I'm going to do is add a else statement to this if here for the proliferating cells. So now what the proliferating cells will do is that if the concentration is below the threshold, they become quiescent. And if it's not below that concentration, they are gonna increase their target volume, which we can remember how to access by asking to edit for the cell attribute target volume. And we are going to increase it by, say, a half every time step. And we also want to do something similar here inside the quiescent cell loops, because, well, some of them just became proliferating. So inside of that, if that changes the time to prolif, I'm just copying over the growth in target volume. So now if I let this run again, and I don't know why CompuCell keeps forgetting that I want 3 cell fields, not 2. We can see that the proliferating cells are getting larger, and so the whole tumor is getting larger. And we start seeing cell division and so on. One thing that I have noted here is that after I did this change in rehabilitated growth, I changed the threshold a little bit, because we see that the proliferating layer is actually quite thin. It's only 1 cell deep, and here for a while it wasn't even 1 cell deep. So what I'm going to do here is I'm going to change my PQ to be 80% of what it was. So I'm just going to multiply everything by 0.8. And yeah, I'm definitely going to need more than 10 minutes. So now we have growth again, and again I changed the threshold here. And again, the code that I uploaded looks a bit different, but it's not. It just looks different. And actually, it's the code that we see here on my presentation. But what's the difference, really? We have a if statement, if a concentration, which is here and here, it's the same number, is less than a number that in that code there is saved in the self-pq handle, but here it's saved inside the dictionary do something. So it's really the same code. And we can see that since we have growth, but our necrotic cells aren't really dying, the whole space fills up. And because this version doesn't have the slightly adjusted threshold for quiescence, the proliferating layer is a bit thin. So now we see that the proliferating layer is way thicker. It's 3 cells, which is about what we wanted before. But okay, we are telling cells to become necrotic, but we are not actually doing anything with that. We have to actually, well, if I just let this run for a while, we're going to see the 3 layers again. But the central layer just stays there, chilling instead of dying. So we have a few options on how to kill our necrotic cells. We have 4 options, but I'm only gonna tell you of 3 of those. You can see the third here, I think. No, here. In the cell manipulation menu. We can either set their target volume to be 0. In that case, from the point of view of the algorithm, the necrotic cells are going to pull everything in. Or we could set their lambda volume to be 0. In that case, the necrotic cells would behave like a foam and would slowly peter out. Or we could slowly decrease the necrotic cells target volume. And what we are going to do is set their target volume to 0, because this is way more fun than this. So here is lambda 0. We see that the tumor eventually invades everything, but it's kind of boring. While here with the target volume 0, we have this interesting pulsating behavior. Are you sure you are trying to increase the target volume instead of the volume?
Can we freeze them?
We could, but I mean, the necrotic cells should, I guess, disappear. Yep, if it's frozen, they won't disappear. So here, when they become necrotic, what I'm going to do is I'm gonna copy this line over, but instead of growing them by 0.5, I'm just gonna set that to 0. And it should result in something cool like this. So if I stop this, restart, and we go. Still in the growth regime. Cell adhesion still applies. So if if we look here, not in the steppable, you'd need to create a cell type that is frozen and change to that. Here we have necrotic contact energies, quiescent necrotic, and so on. So we see that indeed the necrotic cells shrink, but the simulation is kind of slow to run. That's why I have a ton of GIFs here on the left. So cool, now we have a vascular tumor that has the 3 layers and behaves somewhat realistically. But we are not actually, the cells aren't actually feeding, they are not consuming from the nutrient simply decaying inside of them. So we could instead uptake from the field and use that for growth and to set the transitions from one type to the next. But there is one thing about uptake that I think Josh mentioned yesterday, that we could naively assume that we could just take some amount from the field. But that has problems because computers are very literal. Some could say dumb. And if you try to take out 10 units out of a concentration of 1 unit, you end up with negative concentrations. So what is usually done is that we take a percentage of the available concentration instead of just a number straight up. And in CompuCell, by default, all of our uptake functions are of this form. So it takes a percentage. So not only it takes a percentage of the concentration, but there's also a upper limit of concentration you can uptake each time step, which again makes sense. Cells take time to get the nutrient in and actually send it to the mitochondria and do stuff with the molecules. And again, I think Josh mentioned yesterday, we have several options of uptaking just outside the cell, just inside the cell, in the center of mass of the cell, over the whole cell. We're gonna do over the whole cell. But I think this is a good point to add a pause, and we can carry on from here after lunch. So I'm gonna bring back the code. Yep, I'll upload this to that drive right now before I forget. So one nice thing of Twedit is that it also knows how to zip your project. Then to open Jupyter, this might take a little while to open. Let me stop the share here. Oh, a quick parenthesis as well. So one nice thing about using Medium as a supplier is that we could calculate what is the tumor size limit based on the size of the lattice and the size of the tumor.